Have you ever wondered how galaxies formed? To answer that, we must travel back in time to the very dawn of the universe. Picture a time when everything that now fills the cosmos was compressed into a single, incredibly dense point. This was the moment of the Big Bang, the birth of the universe as we know it. In a fraction of a second, this point began to rapidly expand, spewing out matter and energy in all directions. This chaotic, ultra-hot plasma was the primordial soup from which everything in the universe would eventually emerge. As the universe cooled and expanded, matter began to form, creating a sea of particles. It was within this sea that the first seeds of what would become galaxies were sown. From this primordial soup, the stage was set for the formation of galaxies. The cosmic microwave background radiation, or CMB, serves as a snapshot of the universe in its infancy. This radiation is a relic from the Big Bang, the event that kick-started our universe around 14 billion years ago. It's like an echo from the past, whispering secrets about the early universe to those who can decipher them. The CMB is not just a static picture. It tells us about the uniformity of the early universe, showing it was remarkably the same in all directions. But it also reveals tiny ripples of density fluctuations. These minute variations are incredibly significant. They are the seeds from which all cosmic structures, including galaxies, grew. By studying the CMB, scientists can trace back the origins of the universe to the tiniest fraction of a second after the Big Bang. The CMB is a window into the past, giving us clues about the early universe and how galaxies began to form. To understand galaxy formation, we must delve into the mysterious world of dark matter. Dark matter, despite its elusive nature, plays a crucial role in the grand cosmic dance of galaxy formation. It's a bit like the invisible puppet master of the universe, pulling the strings of cosmic structures without ever showing itself. Now you might wonder, how does something we can't even see influence the formation of galaxies? Well, it's all about gravity. Dark matter, though unseen, has mass, and mass means gravity. It's this gravitational influence that helped shape the universe as we know it. In the early universe, dark matter clumped together to form vast halos. These halos served as cosmic seeds, providing the gravitational pull necessary to draw in ordinary matter, the stuff we're made of, and can actually see. Gas, dust, and other particles were drawn into these dark matter halos, forming the first building blocks of galaxies. But dark matter doesn't just help kickstart the process of galaxy formation, it continues to shape galaxies throughout their lifetime. The gravitational pull of dark matter can cause galaxies to rotate, collide, and merge, leading to the diverse range of galaxies we see in the universe today. However, dark matter is not without its mysteries. Despite its evident gravitational effects, we still don't know exactly what it's made of. Scientists believe it's a type of particle that's yet to be discovered. Research into this enigmatic substance is ongoing, and every new discovery brings us one step closer to understanding the fundamental nature of our universe. Dark matter, then, is a key player in the cosmic story of galaxy formation. Its gravitational influence has guided the evolution of the universe, shaping galaxies and driving their interactions. It's a reminder that not everything is as it seems in the cosmos, and that sometimes the most influential forces are those we can't see. Despite being invisible, dark matter played an instrumental role in the formation of galaxies. From these vast cosmic structures, protogalactic clouds began to form. These clouds, composed of gas and dust, were the seeds of what would eventually become galaxies, the colossal systems of stars, planets, and other celestial bodies that populate our universe. The formation of these protogalactic clouds was a pivotal moment in cosmic history. As the universe continued to expand and cool, regions of slightly higher density started to pull in surrounding matter through the force of gravity. These regions became denser and denser, eventually collapsing under their own gravity to form protogalactic clouds. But how did these clouds evolve into the galaxies we see today? The key lies in the conditions within these clouds. They were not just composed of ordinary matter, but also dark matter, a mysterious substance that makes up about 85% of the matter in the universe. Dark matter doesn't interact with light or other forms of electromagnetic radiation, but it does have a gravitational pull. This gravitational pull helped to hold the protogalactic clouds together, allowing them to accumulate more and more matter. As these clouds grew denser, the gas within them started to cool and condense, forming clumps of matter. These clumps continued to grow, and when they reached a critical size, the pressure and temperature at their cores ignited nuclear fusion, giving birth to the first stars. These stars were unlike anything we see in the universe today. They were much larger, brighter, and hotter, burning through their nuclear fuel at an incredible rate. Yet their lives lives were short-lived, ending in spectacular supernova explosions that enriched the surrounding gas with heavier elements. These supernovae also triggered the formation of new stars, creating a cycle of star birth and death that gradually built up the stellar populations of galaxies. These first stars ignited the cosmic dark ages, paving the way for galaxies to form. The birth of these stars marked the end of the universe's dark ages and the beginning of the cosmic epoch known as reionization, setting the stage for the formation of the galaxies we see today. Galaxies are not static entities, they evolve through interactions and mergers. Now you might be wondering, what exactly does it mean for galaxies to interact and merge? Well, imagine two galaxies, each a whirlpool of billions of stars, gas, and dark matter. As they come close to each other, the force of gravity kicks in. It tugs and pulls, distorting the galaxy's shapes and causing a celestial dance that can span over hundreds of millions of years. This process, known as galactic interaction, can trigger new stars' formation and even reshape galaxies entirely. Sometimes these interactions can lead to a more dramatic event, a galaxy merger. This is no ordinary dance, it's a cosmic collision on an unimaginable scale. In a merger, two galaxies come so close that they eventually coalesce to form a single, larger galaxy. This process is a fundamental mechanism in the universe, helping to build up galaxies from smaller pieces in the early universe to the majestic structures we see today. Gravity is the choreographer of these cosmic dances. It's the force that draws galaxies together and shapes the outcome of their encounters. When galaxies merge, their dark matter halos combine, creating a larger gravitational well that can attract even more matter. But these mergers and interactions aren't just about destruction, they're also creators. They trigger bursts of star formation, fuel supermassive black holes, and even create new structures within galaxies. For instance, our own Milky Way galaxy's central bulge, a dense region of stars at its center, is thought to have been formed through a past merger event. It's a captivating process, isn't it? These interactions and mergers are a testament to the dynamic nature of the cosmos. They're reminders that while galaxies may seem unchanging through a human lifespan, they're constantly evolving on cosmic timescales, shaped by the complex interplay of matter and gravity. Through these cosmic dances, galaxies grow and evolve, creating the diverse universe we see today. At the heart of most galaxies lurks a supermassive black hole. These celestial entities, millions to billions times heavier than our sun, reside in the mysterious dark centers of galaxies. But how do they influence the galaxies they inhabit? Well, supermassive black holes play a significant role in the formation and evolution of galaxies. They're like the unseen puppet masters, pulling the strings and shaping the grand cosmic dance around them. When matter falls into a black hole, it forms an accretion disk around the event horizon, the point of no return. This process releases a tremendous amount of energy, often outshining all the stars in the galaxy. But it's not just about bringing light to the darkness. These energy emissions, often in the form of jets shooting out from the poles of the black hole, can influence the surrounding gas and dust. They can trigger the formation of new stars, sculpting the galaxy into its unique shape and structure. Yet, the influence of supermassive black holes isn't always constructive. The same jets that can trigger star formation can also blow away the gas and dust needed for new stars to form. This can halt star formation in its tracks, causing the galaxy to age prematurely. Moreover, the gravitational pull of these black holes can stir up the orbits of stars, creating a bustling hub of activity in the galaxy's core. This can lead to dynamic interactions, with stars being flung out into the cosmic void or spiraling inward to their doom. The relationship between supermassive black holes and their host galaxies is complex and multifaceted. It's a dance of creation and destruction, a balance of forces that shapes the life and death of galaxies. So, while we may think of black holes as monstrous devourers of matter, they are also creators and shapers of cosmic structures. They are integral to the story of galaxies, from their fiery beginnings to their eventual quiet ends. Supermassive black holes, while destructive, play a crucial role in shaping galaxies. They are the paradoxical architects of the cosmos, shaping the universe as we know it. Our understanding of galaxy formation is built on a combination of observational evidence and computer simulations. There's a saying that seeing is believing, and in the world of astronomy, it's no different. For years, our understanding of galaxies has been shaped by what we've directly observed. This observational evidence comes from a multitude of sources, including the Hubble Space Telescope, which has provided breathtaking images of galaxies near and far. These observations offer a snapshot of galaxies at different stages of their life cycles, allowing us to piece together a timeline of galaxy formation and evolution. One of the key pieces of observational evidence supporting galaxy formation theories is the cosmic microwave background radiation. This is the afterglow of the Big Bang and reveals tiny fluctuations in the density of the early universe. These ripples are the seeds of galaxies, and their discovery provided a major boost to our understanding of how galaxies formed. But observations alone can only tell us so much. To truly understand the complex processes involved in galaxy formation, we need to recreate them, and that's where computer simulations come in. These simulations use the laws of physics to model the behavior of matter over billions of years. They start with the conditions of the early universe as we understand them, and then let the simulation run, allowing galaxies to form naturally. This can help us understand why galaxies have different shapes, how they evolve, and what role dark matter plays in their formation. But creating a simulation that accurately reflects the universe is no easy task. It requires a deep understanding of physics, a massive amount of computational power, and a lot of fine-tuning. But when successful, these simulations can provide stunning insights into our universe. Through these tools, we continue to unravel the mysteries of galaxy formation. As technology continues to advance, our observations become more detailed, and our simulations more accurate. Each new discovery brings us one step closer to understanding the cosmic tapestry of galaxies and their place in the universe. Galaxies are not static, they evolve over billions of years. Just like living organisms, galaxies have a life cycle. They're born, they mature, and eventually, they die. This process, however, is not as morose as it sounds. In fact, it's through this evolution that galaxies transform into the diverse celestial bodies we observe today. First, let's talk about their birth. Galactic birth is a grand spectacle, a cosmic ballet of gas, dust, and dark matter. These components come together under the influence of gravity, forming protogalactic clouds. These clouds then undergo a period of rapid star formation, birthing a new galaxy. As galaxies mature, they continue to evolve and change. Star formation slows down, and the galaxy's structure solidifies, taking on one of the distinct shapes we recognize: spiral, elliptical, or irregular. The exact shape and structure a galaxy takes on depends on a variety of factors, including its initial conditions, the environment it's in, and the interactions it has with other galaxies. Speaking of interactions, these play a significant role in a galaxy's life. Galaxies are not isolated islands in the cosmos. They interact with each other through processes like merging and cannibalism. Yes, you heard it right, galaxies can eat each other. In a process known as galactic cannibalism, a larger galaxy can absorb a smaller one, incorporating its stars and gas into its own structure. These interactions can dramatically change a galaxy's shape and size. Lastly, galaxies eventually meet their end. But don't worry, this isn't a fiery explosion or a dramatic collapse. Instead, galaxies simply fade away. As they exhaust their supply of gas, they stop forming new stars. Over time, their existing stars die out and the galaxy becomes a ghost of its former self. From their birth to their present state, galaxies have undergone a remarkable journey. Each galaxy we see in the night sky has a unique story to tell, a story of birth, growth, interaction, and eventual decline. This grand tale of cosmic evolution is what makes galaxies so fascinating, and why understanding them is key to unraveling the mysteries of the universe. The story of galaxy formation is a tale of cosmic evolution. From the Big Bang to the present day, we've journeyed through time and space, from the birth of the universe to the cosmic microwave background radiation, the role of dark matter, and the formation of protogalactic clouds and the first stars. We've seen how galaxies merge and interact, and the critical role supermassive black holes play in shaping galaxies. We've delved into the invaluable observational evidence and computer simulations that help us understand these celestial structures, and we've seen how galaxies evolve over time, influenced by dark matter and other cosmic forces. But this is only the beginning. Research into galaxy formation is ongoing, with new discoveries around every corner. Our understanding of the universe is always expanding, just like the cosmos itself. As we continue to explore the cosmos, who knows what new mysteries we'll uncover about our galactic origins.